looking at inverses of functions. So an inverse of a function is what undoes a function, right? The inverse of adding 3, subtract. It undoes what you just did. Right? We talked about square rooting being the opposite of squaring. Although it's a little bit, it's like one of those ones that has something special involved, because we have to do that plus or minus. So we're going to look at when we can do things straightforward and when it's specials. We're going to skip the construct the understanding today, and I'm going to just get you to take out your highlighter. This is the top of page 237. Okay. I'm going to highlight some notation. So here's the notation for the inverse function. We say f inverse of x. And what happens in the inverse function, graphically, is that if you took a function and reflected it in the line y equals x, what's going to happen is every point on your original function, you just switch the x and y values to find a point on your new function. And that new function will be the inverse. If that new function, sometimes it's not a function, that new thing, that new relation will be an inverse. If that relation is also a function, then we would say it is an inverse function. So here I have a line 2x plus 4. It says that the inverse is a half x minus 2. Right? If I said, hey, I have a number, I want you to multiply it by 2 and add 4. If your answer was 12, what number did you start with? You would have to undo what I just told you, right? If I said you had a number, you multiplied by 2 and you added 4, and then I say, well, your answer was 12. How did you get, what was your original number? You'd have to undo it. And when you undo it, you have to undo it in the opposite order, right? So does it make sense if I multiplied by 2 and added 4, if I wanted to undo it, I'd have to first subtract 4 and then divide by 2. That would undo multiplying by 2 and adding 4. Now I'd have to first subtract 4, so I put it in brackets, and then divide by 2. Now we're going to say, and some of these are going to be so complicated that thinking it through is going to be too much thinking. This is nice that you could probably do that in your head. But we're going to say, well, if an inverse is just switching x and y, then algebraically, if this is my y and this is my x, I just switch them. And if I switch them, and now try to get the y by itself, which is what you did at the getting started part, right? I'd have to move the 4 over, do it slowly. Then I'd have to divide both sides by 2. I could put this in brackets if I wanted. You see that I got this. What did the textbook do, or what did the answer do here? They said dividing by 2 is the same as a half. Would you agree with that? Multiplying by half is the same as dividing by 2. So I have a half times the x, and I also have the half times the minus 4, which made a minus 2. So they took that and simplified it. Me personally, I like what I circled because it really says doing the opposite of what we did to begin with. If first I multiply by 2 and then added 4, if I'm walking backwards, I'd subtract 4 and then I divide by 2. Makes sense. And that's what an inverse is, but it's kind of cool that you can find it by just switching the x and y. And that's going to be a huge idea. So we're going to look at inverse stuff with graphs, with equations, with algebra. Here's the graph of g of x. Sketch its inverse. So a couple of things we can do for sketching its inverse, and I'm going to sketch it on the same one. First of all, you can look at any point, and this one looks like it has 4 key points. So I've got on the red graph, negative 4 comma 4. I've got negative 1 comma negative 1. I've got 1 comma 3. And I've got 3 comma 2. And if the inverse just means that your x's and y's switch, this happens to these points. Instead of negative 4 comma 4, I now have 4, negative 4. And instead of negative 1, I now have, negative 1, negative 1. Because if you switch those ones, if I switch the x and y, it still stays the same. But 1 comma 3 will be 3 comma 1, and 3 comma 2 will be 2 comma 3. So that's switching the points. Next, we have to connect those points. And sometimes that can be hard, because you're like, what order do I connect them in? So another way to visualize things is that an inverse is always a reflection over the diagonal line. I'll draw it with a dotted line here. This is the diagonal line y equals x. So if I take that red graph and flip it or reflect it over the green line, I should get my inverse. I will tell you, for your brain is actually pretty good at reflecting things vertically, and your brain's pretty good at reflecting things horizontally. If you take that and turn it on its side, your brain goes, oh, this hurts a little bit. It's just not used to it as much. You can. You can cheat on the exam. If you get that diagonal line, just take your paper, turn it until that diagonal line is horizontal, then flip it, and then turn it back, and they'll never know. But now that it's flipped, can you see that I flipped this over? This is how I would have to connect them. Can you see this side flips over here, flipping over that line? It kind of gives you an idea how to connect them. I mean, another thing you could use when trying to connect those dots is you could say, well, 3, 2 was connected to 1, 3. So that means now that 3, 1 has to be connected to 2, 3. The same things have to be connected afterwards. So this creates our inverse image. Is the inverse a function? Do you remember how to tell if something was a function or not? The answer to this is no. And we use something called the vertical line test. You might remember this once I mention it and once I show it to you. The vertical line test works like this. If you take a vertical line and you move it across your graph, there we go. If I move it from left to right across the graph, if that vertical line ever hits a graph more than once, it is not a function. So look at the red graph. I'm going along the red graph. I'm hitting the red graph only once, only once, only once, only once, only once. I never hit it twice. The red graph is a function. But if I go across the blue graph, I'm like, everything's okay until like here. Then I hit 2 points. Now I'm hitting 3 points. Now I'm hitting 2, like, and it just has to happen once. You just have to hit 2 points somewhere once, and you can go, nope, not a function. If I wanted to make the red one not a function, I could just add a dot right here. No longer a function, because at that point, it would hit 2 points. And would no longer be a function. Okay, so not a function, use the vertical line test. If you had to explain it and you just said use the vertical line test on the final exam, they would be like, do you really know what is that? You didn't really explain what that means. So there exists an x value with more than one, right? As soon as it hits two things, the vertical line is just going through x values. It's just trying different x values. And as soon as you hit an x value that hits two y values, that makes it not a function anymore. And we like functions because we use our calculator. Our calculator uses functions. When you type something in, it tells you one answer. It'd be very frustrating if it told you multiple answers. Right? It'd be like, and for some things in math this year, we're going to learn that there's an infinite amount of answers. If you typed that into your calculator and pushed enter, and it just started scrolling through infinite amount of answers and didn't ever stop until you opened the back and took a battery out, that'd be frustrating. So we have calculators that function, they always give one answer. That's the goal of our calculator. When there are more than one answers, then we figure that out. Right? Okay. So, state the domain and range of each function. So the red one's domain, its smallest x value is -4, and its biggest x value is 3. And the range, the smallest y value is -1, and the biggest y value is 4. Then, when we look at the inverse, our domain, the smallest x value is -1, and the biggest x value is 4. And the smallest y value is -4, and now the biggest y value is 3. And I want you to notice this. Inverses is all about switching x's and y's. If you switch x's and y's, does it make sense that the x's, the domain of your original one, switched and became the y's, the range of your inverse? And the range of your original one, the y value, switched and became the domain of your inverse. So, you're going to see an inverse question. An inverse question for you will trigger, I should switch x and y. I can switch x and y with points. I can switch x and y with equations. I can switch x and y with domain and range. And it should also trigger for you that it's a reflection over that diagonal line y equals x. And if you think about the line y equals x, every point on that green line would have the same x value and the same y value. Would you agree? Like you'd have 2, 2, 3, 3, -1, -1. And we notice -1, -1 didn't change. Obviously, because it's on that line. We can call that, they have a name for these points that don't change, an invariant point. Vary means change. The in part, sort of a not changing point. But we'll use a fancy word that we don't use very often, just to keep you on your toes. So because it doesn't change, we call it an invariant point. And those are often very important. In fact, on the final exam, they might be checking, did you have that cross in the right place? Because if you were lazy and if you really struggle with connecting the dot and what like that, that's not a very straight line. It might be like, it's not crossing at the right point. Depending on the exam, sometimes they'll go, this year that's a half mark deduction. So, again, those little details are important. Okay, questions to circle on this one? Are 4 and 9. I think they were trying to plan fire drills sometime at the end of this week, but I think it's supposed to rain this morning. So it may or may not happen. But if a fire drill does happen in this class, we use logic and go out the nearest doors, which are there, and then meet in the staff parking lot. And my class just meets in the first row and we just make a nice straight line. and we count that. So, like that. But I think it's supposed to rain. They don't like to practice fire drills in the rain. So when there's bad weather and there's a fire drill, well, it's not a fire drill problem. When there's a fire alarm, then you know something actually happened. We had one year minus 30. Someone put their lunch in the microwave for 18 minutes. And somewhere around the 12 to 15 minute mark, smoke began to come out of the microwave. And then a fire alarm went off. Not a good thing.